Welcome everybody to this new session of the Chilean Probability Seminar. We are lucky to have with us Oliver Kelsey, and now I'm doubting, is it Kelsey or Star?
It's double barreled, but I go with Oliver Tough.
Okay, Oliver Star. So I met him in Bath recent enough, 1 week after inviting him, and he's a really nice guy, and he decided to present with us this work on the selection principles of for the N-branching Brownian motion and the Fleming-Viot process. So the floor is yours, or the...
Yeah, so I'm going to talk about the N-BBM and the Fleming-Viot process. And so let's just start with some basic definitions. So what is the N-BBM? Roughly, you take branching Brownian motions. So these are Brownian motions. They sort of evolve continuously in time. And they branch at rate 1, each particle. And whenever one of the particles branches, you kill off the leftmost. So here, particle 3 branches, and simultaneously you kill off the leftmost particle. Here, particle 2 branches, and simultaneously you kill off the leftmost particle. And the effect of this kind of selecting one particle to die means that the number of particles remains fixed, and it stays as an n-particle system, where n is some parameter, the number of particles. Of course, you could choose different mechanisms for which particle dies with which probability. You can get more complicated. But here we're sort of trying to understand this sort of the phenomenology. So we start off with just the kind of simplest selection principle one might think of, which is just killing off the leftmost. So this was introduced by Brunet and Derrida in the 90s and 2000s to understand sort of the effect of noise on reaction diffusion equations. So when the number of particles is very large, the particle system corresponds to a PDE. What you can think about is that when you have a system with a lot of particles, you can describe, rather than viewing it as, let's say, a system with 10 to the 6 particles, you instead think of it as having a density. Classically, you might think of a gas, technically you might have 10 to the 23 particles, but really you think of it as having a density rather than loads of particles. And in general, so the PDE you're going to get will be a bit more precise later on, but it's going to be a reaction diffusion equation. And in general, you can change the selection mechanism. You still get a different reaction diffusion equation. And these PDEs that describe the density, these have traveling wave solutions. So what is a traveling wave solution? That means it's a solution of the PDE where at time 0, it looks like this blue wave. And then after a given amount of time, it looks like the same profile shifted by CT to the right. So it's a traveling wave solution is just like a wave form which keeps the same shape but just moves at constant speed to the right. And here you'll see that the PDE has one traveling wave solution for all velocities at least root 2. However, despite there being infinitely many of these traveling wave solutions, only the one with minimal speed is physical. Only the one with speed root 2 is sort of observed, and you might think of it as physical, and all the other ones seem to be in some sense non-physical. And we want to understand why is the traveling wave solution with minimal speed kind of the good one, why are the other ones not good ones, and so forth. And that's the same. You observe the same phenomenology. You can change the selection mechanism. You'll get a different PDE, but the PDE will be of the same form, and your same phenomenology appears where you have an infinitely many traveling wave solutions. The one with minimal speed is what we think of should be the good one. So you get the same sort of phenomenology more generally. Okay, now. If we think about the PDE, we don't have a nice uniqueness of traveling waves. But if we instead think about the particle system, we think about the system on a particle system level, then this is a particle system with a fixed and finite number of particles. So it's a finite dimensional Markov chain. So if you have 10 to 6 particles, this is a 10 to 6 dimensional Markov chain. But in any case, it's a Markov chain on a finite dimensional state space, so you can get a nice unique state distribution rather easily. And so for any fixed number of particles, you have some uniqueness. So for any fixed number of particles, the state distribution is unique, this describing the long-term behavior. And so what we want to show is that the so-called selection problem, which is that when the number of particles is fixed and but large, then the profile of the station distribution of so if you look at the particle system in its station distribution, when the number of particles is large, then that profile looks like the traveling wave with minimal speed. So in some sense, this says that one of the reasons that maybe that the traveling wave with minimal speed is the good one is that it's the one that actually corresponds to the particle system, and that the other traveling waves, in some sense, they're just artifacts of the PDE. They don't actually appear when you think about the system on a particle level, and it only appears out of as sort of an artifact of the PDEs. And we expect the same picture for other particle systems in general. So we expect this sort of to be quite a general phenomena. But this was an open problem for any any sort of particle system of this type, and in particular for the N-BBM and the Fleming-Viot particle systems with drift -1, which we'll be talking about today. I should point out that Groisman and Jonquier have an excellent survey on the problem for this sort of pair of particle systems, their relationship, and the selection problem for them. I should also say that the proof we have for the N-BBM, the proof is going to be quite a general tool from PD theory, and so one could adapt the proof quite easily to other branching selection particle systems, and it would follow in the same way, because we're using sort of general machinery here. So what was known? The selection problem was not known, but what was known as something called a weak selection principle. Now, if we look at the particle system, we can see sometimes we can look at the leftmost. If we see sometimes it moves to the left, sometimes it moves to the right, because Brownian motion sometimes goes to the left, sometimes goes to the right. But in general, it's drifting off to the right because of the effect of the jumps or the killing events. Whenever one of the leftmost particle is killed, another particle branches, and the effect of that can only be that the leftmost particle, the position of the leftmost shifts to the right. So here it's here, and it shifts to the right, and the effect of the jump. And so on average, it's drifting off to the right, and it has a certain speed by Birkhoff's theorem. And in fact, the particle system, however you measure its position, maybe the leftmost, the rightmost, the barycenter, the median, it's going to have a asymptotic speed, which is going to be the same however you measure it. So we're going to call that Vn. Vn is the average speed of the particle system for when the number of particles is n. Now we'll recall that the minimal traveling wave speed is √2. And so the weak selection principle is to show that the Vn, the speed of the average speed of the n particle system, converges to √2 as n goes to infinity. And the first weak selection principle was proven by Bramson et al. In the 80s. About 10 years later, Bunet and Derrida, with sort of their work on the N-BBM, proved something stronger, which is that much stronger, that not only does Vn converge to √2, but you have this large pi squared over √2 log squared n correction. So in some sense, you can be quite precise about what the speed of the n particle system is. And Berard and Guer proved that in around 2010 for the N-branching random walk, and there's a PhD student of Julien Berry-Sticky who's saying the same thing for the N-BBM. So in some sense, even though the spatial distribution of the particles was out of reach, quite a lot was known about the average speed. And so then the fact that this converges to √2 tells you that the other traveling waves can't appear because they're going too fast. But it doesn't tell you that the minimal traveling wave, the traveling wave with minimal speed, does appear. It just says that the speed is the thing you think it should be. Now, let's be a bit more precise about I mean by saying it converges to a PDE. So this was Devet and Reminick for the N-branching random walk, and then Damasio et al. For the N-branching Brownian motion. They showed that if initially the profile of particles approximate u naught of x dx, so the profile u naught, then at time t, the profile of particles approximates the solution of this PDE. So what do we see here? Well, here we have a half Laplacian U. This just reflects the fact that you've got Brownian motions doing Brownian motions, being Brownian motions, and so you have diffusion, heat equation appears. You have a plus U, that reflects the fact that you're branching at rate 1. But then you have this term LT. LT is a free boundary. It corresponds to the leftmost particle of the particle system, and it's actually part of the problem. So the problem is to find both a U and an L satisfying the PDE. And so what we see is along the boundary, along LT, U vanishes. The reason for this is that if you're the leftmost particle, you're being killed at rate n. And n, when n is large, is basically infinite. So you're being killed essentially instantaneously once you become the leftmost particle. And that corresponds to this Dirichlet boundary along LT, which corresponds to the leftmost particle. And then the final thing you need for this PDE to be well posed is that this term saying that the mass stays constant. The mass is always 1. This reflects the fact that the number of particles is conserved. That plays out in the limit as saying that the integral of u from across space for a fixed time is always 1. So here, yeah, this is the conservation of the number of particles. And all of these are enough to produce a well-posed PDE. This was proven a few years ago by Berry-Sticky, Brunet, and Pennington. So this sort of PDE tells you what the particle system looks like when the number of particles is large, at least on the deterministic level. There will be some fluctuations from the fact that the particle system is random. Now, this PDE, one can calculate it. It has traveling wave solutions, and in this case, you can actually just calculate them explicitly, because if you go back and you set dtu equal to 0, or you think about if you just plug in that this is a traveling wave, then what you get out of this is a constant coefficient differential equation. You can just solve this with sort of it's quite simple, and you get a solution for all c at least, or for all velocities at least root 2. What would happen if you try to plug in c less than root 2, you'd get sinusoidal solutions. So the minimal traveling wave, the one you think should be special, is this size biased exponential. And all the other traveling waves, they look like exponentials. But they have slightly heavier tails, so they decay slightly slower. And for c at least root 2, they really are decaying only very, very slightly slower than the size bias, than the minimal traveling wave. So all the other traveling waves have a heavier tail, but only slightly for speeds slightly greater than root 2. And that sort of makes it kind of harder to distinguish between the minimal traveling wave and the other ones. So when I say it has a stationary distribution, what do I mean by that? Well, the particle system is shooting off to the right because of the effect of the jumps. We said it has a drift to the right. And since it has a drift to the right, if you just take a fixed frame of reference, then there's not going to be a stationary distribution. Well, the stationary distribution will just be there's no particles, I guess. But you instead have to think about a moving frame of reference. And there are different moving frames of reference you could take. A natural one is just to take the frame of reference of shifting by the leftmost particle. So you view the particle system from its own leftmost particle. That gives you a markup process on where there's always one particle at 0 and all the other particles are on the positive real line. And then so once you shift by the leftmost, it's easy to show that you have that for any number of particles fixed, you have convergence to a unique stationary distribution as time goes to infinity. So there is some unique stationary distribution for fixed n once you shift by the leftmost particle. Now we can start stating a theorem. We're going to take this psi n, this is our stationary distribution, and we're going to let pi min be the traveling wave with minimal speed. And for each n, we're going to take y1 up to yn distributed like our stationary distribution. So we're going to draw particles from the stationary distribution. And once we do that, we have to turn them into a spatial profile. So we put a Dirac mass at the location of each of these y's and renormalize. So we scale the mass by 1/n, so the mass is 1. So this gives you the spatial profile corresponding to the n particle stationary distribution. A priori, this is a random measure, but what we prove with Julien Beresticki is that as n goes to infinity, this spatial profile converges with clean probability to the deterministic profile given by the traveling wave with minimal speed. So as n goes to infinity, the spatial profile looks with very large probability of the particles looks with very large probability like the traveling wave with minimal speed. Okay. So to summarize, we have convergence along the top. This is for fixed time horizons. As n goes to infinity, the N-BBM goes to solutions of this free boundary PDE. It's an open problem what happens as time goes to infinity for this PDE. Right, the long-term behavior of the PDE is an open problem. For when you fix n, the N-BBM converges as time goes to infinity to this stationary distribution. And then we prove that as n goes to infinity, this stationary distribution converges to the minimal traveling wave. I should say this is a bit surprising because normally when you want to prove this kind of arrow along the bottom, usually one needs to know the arrow along the right-hand side to prove this. But the proof essentially uses we have a workaround, which we'll talk about later, which allows us to prove this arrow without actually knowing this arrow without knowing this arrow. Still, we would like to know when this is true, and we have a conjecture for when we have this right-hand arrow. So when do we have it? Would we expect?
Question?
Yeah, go ahead.
So this minimum traveling wave is also recentered like with -2 or no?
Yeah. So the minimal traveling wave is recentered, so its leftmost tip is at 0.
I see.
Yeah. So we would like to know when do initial conditions in the moving, view of the free boundary PD viewed from the boundary converge to the minimal traveling wave. And so we have a conjecture. One is that we have the following tail bound on the initial condition. So this is saying that the initial condition is decaying no more slowly than e to the minus root 2x. The second one is that the average speed is root 2. And we conjecture that these two things should be equivalent to convergence to the minimal traveling wave. So if you converge to the if the PD converges to the minimal traveling wave, that's equivalent to the average speed of the free boundary for the free boundary PD being root 2, which should be equivalent to this tail bound for the initial condition. And that was proven for the Fisher KPP equation by Bramson in the 80s, which is a sort of reaction diffusion equation of similar form, which is thought to have similar characteristics. Okay. I'll also mention about the genealogy. So Brunet and Derrida made a conjecture for what the genealogy of the N-BBM should be, and they conjectured it should be a Bolthausen-Snitman coalescent. So proving this is proven very hard. There's the two Beresticki's in Schweinsberg for about 10 years ago proved this for near critical branching Brownian motion with near critical drift and absorption at 0. But here you're not taking a particle system, you're taking a branching Brownian motion with some fixed finely chosen drift, and that gives you a lot of independence, and that basically allows you to do calculations, which you can't do once you're looking at a particle system. A few years later, Pascal Maillard proved a lot of the phenomenological picture, for an N-BBM chosen with a very specific initial condition. But still, like this doesn't prove the conjecture. It just sort of it shows that the phenomenon, the heuristic, the Brownian Derrida looks right. And so still this conjecture is still very much open. And really one of the big things needed, or the big thing needed, is to understand the spatial distribution of the particles. This is what really, if you look at the sort of the arguments for this, this is what comes out. And one needs to understand the spatial distribution of the particles in quite a fine way. So here we prove that the spatial distribution looks like the minimal traveling wave pi min of x, at least to leading order, if we just look at the bulk. But what one needs to prove is actually this correction term that's, so if we look here, if we let x be much smaller than log n, we see that this correction term is 1. So over the log n scale, this is 1, and this is what we prove. But one wants to know that if you instead look over the log n scale, so then this correction term is not 1 or 0, it's somewhere in between. It's because sine pi x over log n would then be some fraction of that pi x over log n. Then one needs to prove that the spatial distribution looks like pi min of x times this correction term when you look over the log n scale. Don't know how to prove this yet, but it would be nice to be able to sort of extend what we did to prove this over the log n scale, but I think some new ideas are needed. So, how does the proof work? The first step of the proof is quite easy. You just show that the asymptotic velocity is at most root 2. And for the N-BBM, there's a really almost trivial coupling argument that proves this. You couple to branching Brownian motion, and branching Brownian motion has average speed root 2. Okay, of the tip. But what that then means is that, and in particular, the fact that the velocity of the n-particle system is at most root 2, well, we know from Birkhoff's theorem that the expected distance traveled by the leftmost particle in time t, when you start from the stationary distribution, has to be vnt because of Birkhoff. And this second fact is really the fact that we're using for both parts 2 and part 3. And then the point is you use this fact firstly to prove tightness, so to prove compactness, and then to prove uniqueness. And to this is compactness of the n-particle stationary distributions. And then once you have that, you look at subsequential limits, and you want to show that every subsequential limit can only look like your minimal traveling wave. And so we're going to focus on this third part of the proof. You'll just have to trust me when I say that for technical reasons, it's more convenient in the proof instead center by the median. So rather than centering by the leftmost particle, we center by the median. They're kind of almost equivalent, but for the proof, it makes some technical arguments better. And then what you do is you say, well, draw the particle system centered by its median and look at so I take the stationary distribution of the particle system viewed from its median. I turn that into a empirical measure by putting masses at each particle location. There should be a 1 over n there actually. And then thinking about that as the law of that, so the law of that random measure. So this is sort of a measure on median-centered measures. Now, what I want to show, I know that this is tight, right? So I have compactness for this, and the goal is to understand the subsequential limits of these eta n's. So zeta n is contained in this P of PC of R, where PC of R are median-centered measures. And so I want to know what can I say about subsequential limits. Now, what I want to know is it looks, as n goes to infinity, with very high probability, like the minimal traveling wave centered by its median. Now, the key point here is I take the free boundary PDE. And I think about the free boundary PDE as defining a deterministic flow. And the way it does that is you take the PDE, you start with some initial conditions centered by its median, some deterministic mu. I run the PDE for time t, and then I recenter it by its median. Now that's giving me a new median-centered probability measure. So I take the profile, run the PDE, recenter. That's a deterministic PDE, a deterministic flow. And in fact, I can any subsequential limit I can see has to be stationary under that flow. Why? Well, simply because that flow describes my large n limits. So that flow just defines my limits as n goes to infinity. And because all of my pre-limits, my zeta n's, these are all stationary under the particle system. Therefore, I have stationarity in the limit. And so my subsequential limit zeta has to be an element of P of PC of R, which is stationary under the flow given by the free boundary PDE with median recentering. That's not enough to characterize the limits because if I take any traveling wave, and there are infinitely many, that traveling wave will give you the Dirac mass at that traveling wave, so delta pi, is stationary under the free boundary PDE because every traveling wave is stationary under following the PDE and recentering. It's fixed under that. So there's infinitely many zetas that satisfy one, and so we need more. And what do we need? Well, we need to then look at how far does the leftmost boundary travel in time t, starting from zeta. So zeta a priori is a random initial condition. It's a random initial condition for the PDE. And so we draw mu from that random initial condition, right? And because mu is random, when we solve the PDE for time t, that the randomness of the initial condition gives us randomness of the free boundary. So the distance traveled by the free boundary in time t under the randomness of that initial condition is random, but one can show that it's in expectation, it's at most root 2t. And that's simply the fact that in expectation, the distance traveled by the leftmost particle of the N-BBM, starting in its stationary distribution, is at most root 2t. And so in the limit, the expectation of the distance traveled by the free boundary, in the distance traveled by the free boundary in expectation is at most root 2t. So you get this inequality. And then the key point is to show that 1 and 2 tell you that the only thing you can have is the traveling wave with minimal speed. So we can see that the traveling wave with minimal speed, that satisfies this is equal to 2t, or equal to root 2t, almost surely. So it satisfies this, and it's stationary under phi t. We want to show that's the only thing you can do. And the key point is to think about, well, we're going to have to use the PDE technique. On the left, we see that the PDE that I wrote down earlier. On the right, we see an equivalent form of it. So on the left, this PDE defines like a probability density function, right? It defines a mass. And so one can look at the analogous cumulative density function just by integrating from x to infinity. And when you do that, this heat equation becomes well, it again becomes a heat equation. It just works out nicely like that. The U vanishing along the boundary corresponds to big U, i.e. the CDF, having derivative 0 along the free boundary. The free boundary is the same. And the fact that the mass is always 1 corresponds to big U being 1 along the free boundary. So you can go back and forth by integrating to the right or differentiating to the left to get the CDF version of the PDE. Okay, and then what you need is something called a stretching limit. So this goes back to KPP's original paper in the 30s when they introduced the Fisher KPP equation and they prove this for the Fisher KPP equation. We prove this for the for the free boundary PD we've been talking about today. But so what is it? What is a stretching lemma? So if we look on the right, and we see we've drawn here two profiles, blue and red, and we see that they cross at a single point at 0. Now, suppose I shift the red profile to the left, they cross at a different point. But in both cases, to the left of the crossing, the path is above, and to the right of the crossing, the red path is below. And however you stretch them, to the left of the crossing point, the red is above, and to the right, the red is below. And we say that means that the blue is more stretched than the red. And we can see it literally looks more stretched. It's more stretched out. The stretching lemma says that if we take two initial conditions, U0 and V0, with U0 being more stretched, and then evolve the PD for time t, this UT stays more stretched than VT. So stretchiness is preserved under the flow of the PDE. So if you follow the PDE and you start more stretched, then you stay more stretched. And then this is the main tool we're going to use. So what we're going to do is we're going to compare it to the solution of the PDE with heaviside initial condition. So V is a solution with V0 equals this heaviside. So red is V0. And one can see clearly that anything is more stretched than heaviside. It has to be. Right? So for any U0, U0 is more stretched than V0. And therefore, if you follow for time t, UT is more stretched than VT, where VT is the solution with heaviside initial conditions after time t. Now what we're going to do is we're going to take zeta to be our subsequential limit to be determined. This is the thing we want to show is necessarily the minimal travelling wave. And we're going to draw U from it. We eventually will prove that U is deterministic, drawn from zeta, but we don't know that yet. And once we take the random initial condition with the U0 being like zeta, that means that U0, that means that UT is necessarily more stretched than VT because of this second line. So if we start from zeta, we follow it for time t, we then end up as something more stretched than VT. But zeta is stationary. And since zeta is stationary, UT is distributed like U0. And that means that U is at least as stretched as VT for all t, zeta almost surely. So if you draw from your stationary distribution, you're at least as stretched as VT almost surely, and t is arbitrary. Now, I said we don't know convergence to the minimal travelling wave. We do know for one very special initial condition, that's for heaviside initial condition, by a classical argument of KPP. They're using the stretching limit to prove this for heaviside initial condition, and we just do the same thing. And because we know that this VT is converging to the minimal travelling wave, that means that U is at least as stretched as the minimal travelling wave almost surely. So if we draw U from our stationary distribution, our subsequential limit to be determined, then it's at least as stretched as the minimal travelling wave almost surely. Now we're almost there. If we're more stretched than the minimal travelling wave, then what can we do? We can actually prove that that implies that our free boundary has to travel at least distance root 2t in time t. Why? Because, well, if we take U and we center it so it's 1 at 0, so its free boundary starts at 0, and we take the minimal travelling wave centered so its leftmost point is at its free boundary is at 0, so its leftmost point is at 0. U is more stretched, and therefore U stays above the minimal travelling wave. And therefore the comparison inequality, so this sort of just general PD fact, tells us that since U starts above the pi min, it stays above pi min. And since U stays above pi min, its free boundary has to stay to the right of the free boundary with initial condition pi min. But the free boundary with initial condition pi min is exactly root 2t. So that tells us that the solution with initial condition u more stretched than pi min has to have its free boundary stay to the right of root 2t, right? Which implies this inequality. However, we showed that in expectation, because u was random, so in expectation, the distance traveled by the free boundary is at most root 2t, which implies that it's exactly root 2t. And so you combine these two facts, and that's going to tell us that the free boundary is traveling. Okay, the u is random, but we've shown that its free boundary is actually deterministic with constant speed. And then once you have that, you're done because of, well, there are just some QSD results you can put off from the shelf. Because once the free boundary is traveling at constant speed, you can view it as completely equivalent to Brownian motion with drift minus root 2 by just sort of taking a different frame of reference. And some QSD results from Martinez, Pico, and San Martin tells us that the only thing then that can happen is that u is exactly the minimal traveling wave. And so what we've proven is that for zeta an arbitrary subsequential limit, if we draw u from zeta, then u is with probability 1 is a minimal traveling wave. And so it's the thing we want, and so we've got uniqueness. And so we've shown that any subsequential limit corresponds to the thing we want it to be. Now, this was for the N-BBM. There's another some kind of related particle system with another selection problem coming from the same sort of area. It's called the Fleming-Viot particle system. These were introduced by Birdsey, Hollis, and March in 2000 to provide an approximation method for what are called quasi-stationary distributions, which I'll say a little bit about later. So what here with this particle system, instead of killing the leftmost, what we're going to do is we're going to give particles drift -1. So these evolve as Brownian motion with drift -1. And whenever a particle hits 0, it's killed, and another particle chosen uniformly at random branches. So rather than branching to the right, catalyzing killing of the leftmost, you instead have when the leftmost particle hits 0, that catalyzes another particle branching. And so again, the number of particles is stayed fixed. And if you view the N-BBM from its leftmost particle, you can see the two systems are similar. In this case, the large N, the hydrodynamics, so the description of it for large N is given by branching Brownian motion with drift -1, condition not to hit 0. So to say about that, we just take xt to be Brownian motion with drift -1, and you're going to kill it when it hits 0. And in this case, the analog of traveling waves are what are called quasi-stationary distributions. And so this means that if I draw x0 with initial distribution pi, I run it for time t, and then I condition on never hitting 0, then its distribution stays as pi. It's again got a one-parameter family of quasi-stationary distributions where actually I think Guisman and Jonquier pointed out that these two things are the same. And in fact, the minimal traveling wave is again the size bias and exponential. All the other ones are exponentials with heavier tails. The minimal traveling wave, or pi min, or the minimal QSD, is what's called a Yaglom limit, meaning that if I start from a deterministic initial condition, so from x, I run it for time t and I condition on survival. Then as t goes to infinity, this goes to pi min. It's the attractor for deterministic initial conditions. And this pi min is the analog of the minimal traveling wave. Where this is a thing that you want to show in some senses selected in the same way. Now, the analog of the previous result on convergence of the PDE says that if the particle system at time 0 approximates some deterministic initial condition mu, then at time t, the particle system approximates the distribution of Brownian motion condition not to hit 0 with initial condition mu. So the law of Brownian motion condition not to hit 0 gives you a description of the particle system when the number of particles is very large. Again, it's easy to show that here we don't need to do any recentering. right? Because the particle system doesn't fly off, it stays around zero. Um, and it's easy to show that for fixed n, again, you have convergence to a unique stationary distribution. And that what we do is we draw particles x1 up to xn from this stationary distribution for fixed n. And we prove that as n, and so we turn that into a spatial profile by putting a mass at each particle, renormalizing by 1 over n as before. And we prove that as n goes to infinity, this converges to the minimal quasi-stationary distribution as n goes to infinity. I proved this about a year ago, so this proof of this came before the proof of the N-BBM chronologically. So yeah, so what we see is this essentially the same sort of thing as we're proving for the N-BBM. And
What
so you see
so if you put a different drift, do you have a different pi mean that appears?
a different what?
So if you have a different drift instead of one, does it play a role on the limiting distribution?
Sorry, a different what instead of one?
Drift?
Drift. Oh, no, it doesn't. And in fact, if you change the drift to minus c, it's actually exactly the same thing by rescaling. If you rescale space and time, you can rescale space and time to turn drift minus one into drift minus c. As long as the drift is to the left, it's the same.
So just help me understand. So why there is no the square root 2 appearing here?
Because we have a sort of a different. It's essentially amounts to a different normalization.
I see.
Once you have drift minus one, your branching rate isn't going to be one. I think it's going to be root two or something like that. It's essentially once if you take drift minus one, it amounts to having a slightly different rescaling of space and time. So if you want the Fleming-Viot particle system that really looks like the N-BBM, you'd take drift minus root two.
I see. Thank you.
Yeah, and so you see the same, basically the same sort of picture that the Fleming-Viot process of a fixed time horizon converges to the law of Brownian motion, condition not at zero. Now, Martinez et al., this is not open. Martinez et al. Proved about 25 years ago that when this converges to the minimal quasi-stationary distribution, so it's a sort of a complete description of which mu this works for. Again, it's easy to show for fixed n convergence to a stationary distribution. And then our main result, as before, is that this stationary distribution converges as n goes to infinity to the minimal quasi-stationary distribution. So with large probability, the stationary distribution looks like the minimal quasi-stationary distribution. A bit of background on this so this was introduced to provide an approximation measure for quasi-stationary distributions. With drift minus one, you can calculate it, but that's special. In general, you can't. And they established a similar picture for Brownian motion on bounded domains. However, here the quasi-stationary distribution is unique, and you have uniform convergence of the law of Brownian motion condition not to hit the boundary to it. So there's no selection, and in general, when you have bounded domains, it makes there's some sort of more straightforward arguments that you can make because you have some sort of uniform convergence. So, but on unbounded domains, things get sort of quite a bit more complicated. Asseller, Ferrari, Groisman, and Jonquier proved this for Einstein-Uhlenbeck dynamics with killing at zero. So instead of having drift minus one, you have drift minus x. And here the QSDs are non-unique, and you have a selection principle, but you do have a strong drift, and this allows them to work with Lyapunov functions. However, about a few years ago, Denis Villemone has proven that if you did have such a Lyapunov function, then something is true, which in this case is not true. So you have no hope of getting a Lyapunov function, and it's not going to work. So as a result, these sort of techniques that one would like to use when you have strong drift or some bounded domains break down. Nevertheless, it was sort of thought to be true still with drift minus one. Yeah. So what's the proof strategy? The proof strategy is similar, but the points of the strategy where the difficulties arise is different. So for the N-BBM, the real meat of the proof was the uniqueness part. However, here for the Fleming-Viot process, we can basically take QSD stuff from Martinez et al. Off the shelf, and so the uniqueness part isn't hard. The hard part in this part is 1 and 2, which is firstly, we want to show that the average number of drifts, so we let lambda n be the average number of drifts appropriately renormalized in time t. So if you run the n particle system for a very large number of times, you divide by time and n, then that's lambda n. It's the average number of killing events per unit time. And here one wants to show that the limit of lambda n is at least a half. This is the analog of showing that the average velocity of the n particle system for the N-BBM is at most root 2. So this is much more trickier than for the N-BBM. And then the second part is to then use this to establish tightness, which is also trickier for the N-BBM than for the N-BBM. So we'll focus on sort of 1 and 2. So how do you prove that the limit for lambda n is at least a half? So first thing, like just to start with the definition, we let Jn, this is the average number of jumps up to time t, divided by n. So it's the number of jumps appropriately renormalized. And so lambda n is just the limit as t goes to infinity of jt over t. Of course, this exists by Birkhoff. And what we want to show is, we recall, is this limit for lambda n is at least a half. So what you do is you're going to take a deterministic initial condition. And you can do that. It's enough. You can just take an arbitrary deterministic initial condition and show this and lower bound the average number of jumps per unit time, starting from a deterministic initial condition. But if you know that this is if you know the almost sure limit for any deterministic initial condition, then you know the almost sure limit for any initial condition. But for this argument, it's important to start with a deterministic initial condition. And we're going to let tau 0 be the hitting time of Brownian motion with drift -1 with initial condition given by mu naught. There should be 1 over n here, given from this deterministic initial condition. So you take this x, you turn it into an initial measure, and you use that as a initial distribution for Brownian motion with drift -1. And so the idea is you show that these two terms both satisfy the heat equation. On the right, this is just the distribution of Brownian motion with drift -1 killed when it hits 0. And so it's sort of very classical that this satisfies the heat equation with Dirichlet boundary conditions along 0. When I say the heat equation, it has a minus del dxu term. What you need to but the key point is that by considering the right family of martingales, this functional of the n particle system also satisfies the expectation of this functional of the n particle system also satisfy the heat equation. So what we see here is some exponential of the number of jumps. Right, so this is some compensation term, and then this is like an empirical measure of the particles. And given an expectation, this gives you some biased mean measure. So for any set A, you count the number of particles in A, and then you multiply by the exponential of the number of jumps. So you have these two terms, and just by considering the right family of martingales, you can see that this satisfies the heat equation with Dirichlet boundary conditions and initial condition mu naught. And therefore, by some sort of PDE uniqueness, they have to be the same. Now, once we know this is the same, I can basically integrate up. Right, integrate over 1, integrate over space. So just take the total mass of both left and right. They're the same measure, therefore they have the same mass. Since they have the same mass, that means that this expectation of e to the minus number of jumps is equal to, well, what's the mass of the right-hand side? The mass of the right-hand side is just the probability of survival for Brownian motion with drift -1. And because and this is where we use the fact that we have deterministic initial condition, because X is deterministic, that means that mu naught is compactly supported, and that means the probability of survival is decaying like C e to the minus a half t. And so this the expected value of e to the number of jumps is at most c e to the minus a half t. Right, so you have this equation, and that's it, and that's all. Now you're in the clear. Essentially, if you think back to the proof of Cramer's theorem, there's sort of two directions, but the easy direction is you take the exponential of the sum and then you apply Markov's inequality. And you essentially we're doing the same thing here. So you apply Markov's inequality, and then this term, once you apply Markov's inequality, says that the probability that the number of jumps divided by t is less than a half minus epsilon is decaying exponentially in time. And since it decays exponentially in time, it's summable. And since it's summable, Borel-Cantelli says that the probability that this is less than a half minus epsilon infinitely often is 0. Right? So we've gone from here, knowing this fact about the expected value of the exponential of the number of jumps, to the fact that almost surely, for your arbitrarily chosen initial condition, the average number of jumps per unit time is at least a half minus epsilon. So this is all you need. So this tells us that you're getting enough jumps, and this is sort of the first key piece. And then the second piece is then to use this to prove tightness. Now, the thing to point out here is that you really can't do fine estimates. So if you try to get fine estimates on these particle systems, you kind of get nowhere. And so trying to prove tightness directly by just sort of estimating things about the particle system is actually surprisingly hard. Like you would think that somehow tightness, you could just do some easy calculation and it would work. It doesn't. Well, instead, what you have to do is the following. So you think about the mean measure. So what is the mean measure? The mean measure, you take a general set A, and then you draw from the station distribution, and you count under the station distribution how many particles are in A. All right, so you count the number of particles in A once you've drawn from the station distribution. And then you take that in expectation. And we call that the mean measure. So if you want so what's phi n of the whole space? Well, almost surely all the particles are in the whole space. So the mean measure of the whole space is 1. And it's just a fact that the mean measures being tight implies this sort of random empirical measure. The random measure given by the n particle station distribution is tight. So it's enough to prove tightness of these mean measures. And now what we're going to recall is, well, the limit for the lambda n's is at least a half. So in particular, lambda n is at least a quarter, say. And we point out that the number of jumps over time is converging to n lambda n, almost surely. And since the number of jumps divided by time converges to n lambda n, the nth jump time divided by little n is converging to 1 over n lambda n. So we know this from Birkhoff, and therefore by sort of inverting, you have this second fact. So the nth jump time divided by m is converging to 1 over big N lambda n, where we've got a lower bound on lambda n and hence an upper bound on this. And now this is kind of all we need. Why? Simply because of Birkhoff. So Birkhoff is saying that long time almost sure limits is equal to expectation of the station distribution. And in this case, we know what the long time almost sure limits are, right? We know that the nth jump time divided by little n is converging to 1 over this. And you can trust me that therefore implies by Birkhoff that if we draw from this n particle station distribution and we think about the lifetime of a new particle, the average lifetime of a particle, it has to be 1 over lambda n. And so the expected lifetime of a new particle is 1 over lambda n. And that implies that if we start by sort of taking expectations, Well, it implies that if we draw Brownian motion with drift -1 from our mean measure, the expected value of its lifetime, the time started from the mean measure from the n particle system phi n of Brownian motion with drift -1 killed when it hits 0 is 1 over lambda n. Right? So what have we done here? We've said that we know this fact about the long time about the almost short limits, and we're using that to say something about the expectation of something given the mean measure. Now, just by martingale stuff, you know that the expected time, if you start a brand new motion with drift -1 from x, the expected time for it to hit 0 is just x, just because of martingales. And so what that implies is that this moment, the integral of x phi n, is equal to 1 over lambda n, exactly. And since we've lower bounded lambda n, we've upper bounded 1 over lambda n, so this is particularly it's a most form. And so that's it. Right, once you have an upper bound on the first moment, you have tightness. And so really the whole point of tightness is you prove this fact that from the first part about the almost short limits, and then you use Birkhoff to turn that fact about almost short limits into a fact about first moments. And once you have that fact about first moments, you now know you have tightness. And so we've proven this sort of fact about the first moment without actually knowing anything precise about the particle system, just a fact about the almost short limits. Now, finally, I'll end off with that. What are we using here that's particular to this drift -1? It's a sort of what's it called again? You can replace drift -1 with more general dynamics, and it's a Folk conjecture that in general, if your killed marker process has a Yaglom limit pi min, then perhaps under some technical condition, then the stationary distributions of the Fleming-Viot particle system should approximate pi min as n goes to infinity. So the selection problem is thought to be true in general for Fleming-Viot particle systems. And we've used really very little specific about drift -1, except for one thing in the proof that we do use, is that if we use the fact that for Brownian motion with drift -1, if your probability of survival decays like e to the minus lambda min t, where lambda min is it's like an eigenvalue corresponding to the minimal quasi-stationary distribution. If you start from the minimal quasi-stationary distribution, your killing time is exponential distribution with parameter lambda min. And so we use the fact that if your probability of survival decays like this, then you have convergence to the minimal traveling wave, to the minimal QSD. If one could prove this in general, then one would know that the Folk theorem was true. But this is the only place in the proof where we actually use anything specific about Brownian, about the drift being -1. Because with a drift -1, you can just check that this is true with some known facts. And that's the end.
Thank you very much, Oliver. Are there any questions?
I have a question. Can I?
Of course.
Okay. So first, thank you, Oliver, for this beautiful talk, and congratulations. These problems have been open for several years, so it's very nice to see that now they are solved. I want to ask you a question about the proof of the selection principle of N-BBM. If I understood correctly, what you prove is that if you have a subsequential limit, then when you start with this limit, then it cannot travel at a velocity larger than square root of 2. Is that right?
Yes. So the proof of how do we know that, or what you? Yes.
So is it correct somehow to say that you prove the strong selection principle from the weak selection principle? So you think that maybe it can be proved something like like weak selection principle implies strong selection principle or something like that, or?
I guess so, yes. So what we actually need is we only need the one-way inequality. Um, yeah, and so then that's really all yeah, it's saying that it's somehow from the weak selection principle you can get a strong selection effect.
Sorry, Oliver, could you repeat your answer because there was some noise.
Yes, so I mean, really, yeah, the thing you're using is that Vn is at most root 2. You don't actually need to know that Vn is converging to root 2. Although I guess this is an art of this can be viewed as a consequence. But yeah, all you're really using is the fact that the Vn is at most root 2, and you have this general fact about stretching. And this general fact about stretching is a thing about Fisher KPP equations. So once you have the stretching and then you have the Vn at most root 2, then this is really all you're needing.
Thank you. And you think the proof for N-BBM should hold similarly for other particle systems with this selection mechanism, right?
Yes. Yes. Basically, the only as long as you're working with like a branching selection particle system, you could and you have Vn is you'd have to be working to know that Vn is the most root 2. So I guess this would be the pooled regime. But if you have a pooled particle system, if you know what that means, so if as long as you know that Vn is the most root 2, then you can change up your selection mechanism, and it should be the same. And in general, as long as no particle is branching faster than the tip, then Vn is going to be at most root 2, root 2t. So you could change your selection mechanism, and the same thing it'd all be the same. What would be difficult is we need a stretching lemma, and so the stretching lemma is a fact about Fisher KPP equations with like this half, normal PDEs. If you turn it into a branching random walk, and so you no longer have this PDE, it's not clear that you can get the same stretching lemma. And so it's not clear that maybe a different argument is needed. But at least in the diffusive case, when you have, Brownian motions with some selection, whatever you want, corresponding to some reaction diffusion PDE, then yeah, the argument works the same.
Okay, thank you.
So, are there any other questions?
I have a simple one, but I don't know if it's a short answer. I was just wondering about the proof of tightness for the N-BBM. Is that sort of relatively simple? Because in the proof of uniqueness, it's like there's not too much probability. It's mostly PDE.
Yeah.
So I guess most of the probabilistic part is shoved into the.
Yes. So essentially what you do is you actually have a thing here. If you think about how far the barycenter travels. So the barycenter will travel some distance in time t, but in expectation it's going to be at least it's going to be Vn because of Birkhoff. Right? The average speed is Vn, it's going to travel Vn. And so what you do is, well, you say, well, the expected value of the distance traveled by the barycenter is Vn, but you're going to do a martingale argument where you can write, you can think about the distance traveled by the barycenter here as the distance traveled by all the Brownian motions plus the jumps. Now, if you take an expectation, that just the Brownian motion terms cross out, and you just get the expected value of the distance traveled by the jumps. All right, so in expectation, the distance traveled by the barycenter is the distance traveled by all the jumps. And then you essentially use a martingale argument to see that the expected distance traveled by all the jumps is because when you jump from the leftmost particle to another particle, what's the expected value of how far you travel? Right? You're choosing one of the other particles uniformly at random. And so the expected distance traveled by the leftmost at the jump time is exactly the first moment of the particle system viewed from its leftmost particle. And then by Martingale's and Fabini's theorem, that tells you that the expected value of the expected distance traveled by the jumps, all the jumps up to time t, is going to be exactly mt minus m0, and because using stationarity is exactly the first moment, right? So that shows you is that the first moment of the particle system is exactly VNT, exactly Vn. Because the first moment of the particle system under its station distribution is the expected distance traveled by the barycenter, which is Vn, and therefore the first moment is Vn. This is bounded moments give you tightness. And in some ways, it's similar to the Fleming-Viot in that you're using Birkhoff, basically. Right.
Okay, nice. Thank you.
Just a stupid question to understand the selection mechanism. What happens if instead of erasing the smallest, you erase a random one but put a child of the biggest on the rightmost? Does it change something?
Well, what would happen then is you would have that would amount to having a larger branching rate for the rightmost.
Yes.
And then you would have to check that doesn't increase the average velocity. I think it should be fine because the branching rate is still increasing. So it just means if you make the rightmost particle, it should be the same, but you'd have to check. It's not clear what would happen to the PDE, because in some sense you add.
Let me make one comment. We consider more or less the particle system you described. Abelio, we choose, you do Brownian motion and you choose two particles at random and you make the leftmost one jump on top of the rightmost one. And there you can prove weak selection principle, as Oliver mentioned. And what you get in the limit is exactly the KPP equation. So you get the square root of 2.
Okay, I see.
Yeah, I would say for that particle system, the proof is the same. Yeah.
Thank you. So are there any other questions? So if not, let's thank Oliver again for the great talk. Then we can go to the informal